So I'd like to do some examples now to illustrate what it's like to verify whether or not vectors live in one of the particular 4 subspaces. And keep in mind that it's generally easier to verify whether or not a vector lives in a null space than a column space. So let's see some examples here. So here I have a particular 2 by 3 matrix. And because this matrix is 2 by 3, I can view it as a machine that goes from R3 into R2. So let's say I wanted to verify whether or not a vector lived in the null space of this matrix. All I need to do is take my matrix and multiply by the candidate vector and check whether or not I get 0. So in this equation over here, I'm taking my matrix A, and I'm trying to verify whether or not the vector 1, 1, 1 is in the null space of my matrix. Well, when I multiply my matrix by 1, 1, 1, I produce the vector 6, 12. 6, 12 is certainly not the 0 vector, so the conclusion is that 1, 1, 1 is not in the null space of my matrix. So it's as easy as that. If you want to check whether or not a vector is in the null space, multiply by A, check whether or not you get the 0 vector. And the same fundamental principle applies to the left null space, except now we transpose A before we do the multiplication. So here, I'm trying to verify whether or not the vector 2, negative 1 is in the left null space of my matrix. And the way that I'm going about this is I'm transposing A, so that's this matrix here, and then I'm multiplying by the vector 2, negative 1. And in this case, when I do the multiplication, I get the 0 vector. So this is telling me that the vector 2, negative 1 is in the null space of the transpose, or in the left null space of A. So to check whether or not a vector lives in the null space or the left null space, we either multiply by A or A transpose and check whether or not we produce the 0 vector. And it's generally a little bit more difficult to verify whether or not a vector lives in the column space or the row space. Let's look at an example in the column space. In this calculation, what I'm trying to do is verify whether or not the vector 1, 3 is in the column space of my matrix. According to the Roche-Capelli theorem, what I need to do is I need to augment my matrix with the vector 1, 3, do the row reductions, and look for a pivot in the augmented column. Here I do get a pivot in the augmented column, and this tells me that the vector 1, 3 is not in the column space of my matrix. Let's go to the other side and verify whether or not a particular vector is in the row space of our matrix. So here, I'm trying to test whether or not the vector 3, 9, 6 is in the row space of our matrix. The way to verify this is to transpose the matrix, augment with 3, 9, 6, do the row reductions, and look for a pivot in the augmented column. Here, I get no pivot in the augmented column. This tells me that the vector 3, 9, 6 is in the column space of the transpose, which is also called the row space. So we have 4 generic examples here of what it is like to verify whether or not a vector lives in one of the 4 fundamental subspaces of a matrix. The major takeaway here is that it's easier to solve verification problems using null spaces than it is with column spaces. On the other hand, sometimes what we want to do is not verify whether or not a vector lives in one of the spaces. What we want to do is we want to produce vectors that live in one of the spaces. This is the exact opposite situation. It's generally easier to produce vectors that live in the column space or the row space than it is to produce vectors in the null space or the left null space. So let's see an example illustrating this. So here what I'm doing is I'm looking at the column space of my matrix, and I want to just give an example of something in the column space. Well, what we can do to produce something in the column space is just take any linear combination of the columns, and any linear combination will be in the column space. Here what I'm doing is I'm taking my matrix, and I'm multiplying by the vector 3, 1, negative 2, and when I do this multiplication, I produce the vector 2, 4. This tells me that the vector 2, 4 is in the column space of my matrix. So every time I take my matrix and multiply by a vector, I always produce something in the column space. What if I wanted to produce something in the row space? I do the same thing, except I transpose my matrix first. So to produce something in the row space, I take my matrix, I transpose it, and then I multiply by any vector. Here I'm multiplying the transpose of A by the vector 1, negative 3, and that produces the vector negative 5, negative 15, negative 10. This is telling me that the vector negative 5, negative 15, negative 10 is in the column space of the transpose, which again is called the row space of the matrix. Great. So to produce something in the column space, just multiply your matrix by any vector, and whatever the result is in the column space. To produce something in the row space, you multiply the transpose of your matrix by any vector, and whatever the result is a vector in the row space. But it's generally harder to produce examples of vectors that are in the null space or the left null space. So over here, what we're doing is we're taking our matrix and we're row reducing it. And again, row reductions are computationally expensive. So I did row reductions on my matrix, and I produced the reduced row echelon form. And what I can do is I can use the column relations to find vectors that I can multiply my matrix by to produce the zero vector. So by row reducing my original matrix, what I can do is I can easily see that the second column is 3 times the first. And that tells me that if I multiply my original matrix by negative 3, 1, 0, the result will be the zero vector, which tells me that negative 3, 1, 0 is in the null space of my original matrix. What if I wanted to produce something in the left null space, so the null space of the transpose? Well, what I want to do is I want to calculate the reduced row echelon form of the transpose of my matrix and use that to find vectors I can multiply the transpose by to produce the zero vector. When I row reduce the transpose here, what I find is that the second column of the transpose is twice the first. So if I were to multiply the transpose of my matrix by, say, the vector 2, negative 1, I should produce the zero vector. And that tells me that the vector 2, negative 1 is in the left null space, or the null space of the transpose. So it's always possible to produce examples of something that lives in a null space. It's just that in order to do this generically, we have to row reduce the matrix to get a better understanding of how the columns relate to one another. And that's more expensive than it is to just take our matrix and multiply by a vector to produce an example.